Okay, so we were discussing about the phase modulation, and we have discussed a condition that when we modulate, when we change the angle of the carrier signal with respect to the message signal or the baseband signal, we get a condition called as angle modulation, and in the angle modulation we have phase modulation and frequency modulation. So we were discussing about frequency modulation, that frequency modulation means basically the changes in the phase, the phase modulation, that is changes in the phase of the carrier signal with respect to the baseband signal. And we have derived a very basic equation. See, this equation ST is equals to AC cos 2 pi FCT plus KP times MT. This is the standard equation, okay, standard phase modulated equation. This is our standard phase modulated equation, and by this equation we can put any kind of message signal MT, and based on that we will get a standard signal ST, which is the finally phase modulated signal, because this is basically the carrier signal, and by modulating it by moving this by relating the message signal or the baseband signal to this signal, we get a phase modulated signal. So this is a PM wave. Okay, this is a PM wave, phase modulated wave. Okay, this is the equation of a phase modulated wave. Now moving further, so this is like a basic phase modulated wave. We have understood this. Now moving further, let's see a important conclusion. See, we got this angle or the instantaneous angle as 2 pi FCT plus KP times MT plus phi 0. Okay, this is the angle. Okay, this is the instantaneous angle at any point of time. By putting the value of time, we will get the value of this angle at any point of time, because FC is a constant. It's the frequency of the carrier wave. This is the frequency, okay, and phi is the initial phase angle. So what I can see is, if we differentiate this equation, with respect to time, I will get something like this: d by dt of theta it by dt. Okay, then differentiation of this part with respect to time, and then differentiation of this part with respect to time, and since this is a constant, so this will be 0. So I haven't written it, but you can, if you want, you can write it as 0. Okay, now we can see that if we differentiate this, now what is d theta by dt? Okay, what is d theta by dt? D theta by dt is basically 2 pi f. Okay, 2 pi fit. Now why I am saying this? Because what is d theta by dt? You know that theta is equals to, what we can say, that d theta by dt is basically omega, or omega can be written as 2 pi f. Okay, 2 pi f, 2 pi frequency. So frequency is basically equals to 1 upon 2 pi times d theta by dt. So in place of this d theta by dt, I can write the value 2 pi f is equals to, now by differentiating this part, you will get dt by dt, that's 1. Okay, so dt will be differentiated. 2 pi fc is a constant, so it will come out of the differentiation, so it's 2 pi fc. Now plus by differentiating this, you will get kp as a constant. It's a phase sensitivity, so it will come out as a constant, and ultimately you will get mt as the differentiation. So differentiation of mt, d by dt of mt, we can write it as m dash t. Okay, differentiation of mt will give you m dash t. So this is our m dash t. So by moving this 2 pi, by dividing this equation by 2 pi, you will get that fit is equals to fc plus 1 upon 2 pi kp times m dash t. Now this is known as the instantaneous frequency. Okay, this is basically known as the instantaneous frequency of PM wave. This is the instantaneous frequency of PM wave. That is, we are getting that what exactly the frequency of this frequency modulated wave at any point of time. Now why I am saying this? It's because in case of amplitude modulation, you have seen that there is no change in the frequency or no change in the phase of the carrier signal. It's only the amplitude which gets modulated or changes. But in case of angle modulation, we can get an instantaneous frequency. In case of AM, that is amplitude modulation, the instantaneous frequency will remain FC only. Okay, it will remain FC only in case of amplitude modulation. But if we go for the angle modulation, we'll get the instantaneous frequency. Specifically in the phase modulation, we get the instantaneous frequency as fc plus 1 upon 2 pi kp times m dash t. That is the differentiation of mt, the baseband signal. So this is like the phase modulated wave. Okay, this is the frequency of the phase modulated wave. So we have derived two things. One is the equation of the phase modulated wave and the equation of the frequency of the phase modulated wave. Okay. Now moving further, let's talk about the frequency modulation. Now what is basically the frequency modulation? Now as I told you, in case of phase modulation, we are going to change the phase of the carrier signal with respect to the baseband signal. But in case if I talk about the frequency modulation, we are going to change the frequency of the carrier signal. Okay, I will say that frequency of carrier signal will be modified. Okay, the frequency of the carrier signal will be modified. So here I can see that the frequency, I can write it as frequency of the frequency of the phase frequency modulated wave, that is FM wave. It is FIT is equals to FC plus KF times MT. Now FI means instantaneous frequency, that the frequency at any point of time. If I put the value of time, I will get the value of frequency. Okay, you can see this message signal, it is varying with time. So by putting the value of time at any instant of time, I can get the frequency of an FM wave. Now here we can see FC is basically the constant, the frequency of the constant or the carrier signal. Okay, it's a constant initially, the frequency. And you can see KF is written here. Now what is KF? KF is basically the frequency sensitivity. Now frequency sensitivity means that how much our FM wave is sensitive to the message wave, to the change in the message wave. Okay, so we can see that if KF is greater, then the change or the sensitivity of the frequency modulated wave would be more. That is, if a small change in message signal happens, that can be reflected in the frequency modulated wave. Okay, if KF is very small, then the changes wouldn't affect the frequency modulated wave. But in this case, we can see, since this KF represents the frequency sensitivity, okay, the sensitivity of the frequency. Now if I talk about the unit of this KF, what can be the unit? See, the unit of MT is volts. Okay, and the unit of KF times MT, what should be the unit of KF times MT? I can see this is frequency, this is frequency, so this has to be also in frequency, that is in hertz. Okay, that is in hertz. So what can be the unit of MT what can be the unit of KF if I specifically talk about? You can see that if I shift this KF in the denominator, I will get that unit of KF is hertz per volt. Okay, it's hertz per volt. This is the unit of frequency sensitivity. Now in the phase modulated, we have seen the phase sensitivity and the unit is radians per volt, but in this case we are discussing about frequency, so it's hertz per volt. Moving further, now I can see that in place of this Fi, I can write this 1 upon 2 pi d theta by dt. Okay, right now just we have discussed that d theta by dt, which is equals to omega, which is equals to 2 pi f. So I have shifted this 2 pi in the denominator, and f, I can put this f as 1 upon 2 pi d theta by dt, okay, is equals to f plus kf into mt. Okay, now if I shift this 2 pi in this RHS from LHS to RHS, I will get the condition that d theta by dt is equals to 2 pi fc plus 2 pi kf into mt. Okay, now if I move this d theta, or if I can say that I can integrate this equation, this is like an equation in which I can shift this dt to the LHS, from LHS to the RHS, I can get an equation like this, that d theta is equals to 2 pi fc into dt plus 2 pi kf into mt dt. Okay, I am simply shifted this dt from LHS to RHS. Now we can get this equation. See, observe this equation very carefully. Okay, you will find that this equation is written in terms of phase. Okay, a small change in phase is equals to a small time period, and this is again a small time period, and the instantaneous value of the message signal. Okay, now if I integrate this equation, okay, in this equation we got this equation. and if I integrate this equation, I will get that integration of dt, integration of d theta is equals to 2 pi fc, and it will be constant, so it will come out of the integration. We get integration of dt plus 2 pi kf into mt dt. Okay, now if I integrate this, I will get that d theta, or I can say that d theta gets integrated and it will become theta t. So it is equals to 2 pi fc into t plus 2 pi kf into mt dt, and this mt will be integrated over from minus infinity to t. That is the complete time period at the instantaneous, at what point of time I am talking about. So at that point of time, whatever the value of mt, it will be integrated over the period of minus infinity to t. Okay, so what we are basically getting, we are getting the angle, okay, the instantaneous angle. This is representing the instantaneous angle of a frequency modulated wave. Okay, this is representing the instantaneous angle of an FM wave. Okay, it is representing the instantaneous angle of an FM wave. Now what I can see that the message signal or the carrier signal can be written as, see, this is our carrier signal, st is equals to AC cos I theta, okay, theta it. So in place of theta it, if I write the value, this one, if I write the value this, so this will become AC is equals to cos 2 pi fct plus this value, okay, 2 pi kf into integration of from mt dt from minus infinity to t. So what this equation is basically representing, this is the instantaneous, or we can say the standard equation. Let me correct it. This is the standard equation of frequency modulated wave. This is what it's the standard equation of frequency modulated wave. Okay, an FM wave is formed in by using this type of equation. Okay, it's the mathematical representation of a frequency modulated wave. Now coming to the point that how the graphically, how diagrammatically this amplitude modulated waves look like, how the phase modulated wave or frequency modulated wave will look like. So let's see about the amplitude modulated wave. Sorry, I can see that amplitude modulated wave, for example, this is my modulating signal. Okay, let us suppose this is my modulating signal. Let us take another pen. So like this is my modulating signal. You can see here it's a simple sinusoidal wave. Okay, and we have this carrier wave with high frequency. You can see this, the frequency of the carrier wave is very, very high, okay, compared to the modulating signal, okay, the baseband signal. Now when you overlap this, okay, when you go for the amplitude modulation, when these two signals interact, the amplitude modulated wave will form something like this. Okay, that is, the amplitude of this carrier wave will move along with the modulating signal, okay, with the amplitude of this modulating signal. You can see here like this amplitude modulated wave, when the signal is getting increased, when it is increasing from this point, let's say this is 1 and this is 2, okay, and this is 3. So when it is increasing from 1 to 2, the final signal, our amplitude modulated signal, will also start from 0, or we can say the 1, and it will increase till the point 2 is reached. Okay, till the point 2 is reached, like this, somewhere here. And when from 2 to 3 it is getting decreased, so 2 to 3 it will going to decrease and it will fall somewhere here, like this. Okay, and then you can see what is happening is from 3 to, let us suppose this is 4, this is increasing in the downward direction, or this is increasing in the negative direction. So our signal will also going to increase in the negative direction, and at some point of this instance, like this is 4. So from 3 to 4 it is getting decreased, and then from 4 to 5, let us suppose this is 5. So from 4 to 5 what you are getting is, from 4 to 5 it is increasing in the positive direction. So it is getting increased and it will reach the point 0. So this is the 5. Okay. Now the point here that we have seen is that when we are going for the amplitude modulation, we do not get only a single wave. We get an envelope like this, an envelope completely in this way, like this. Okay. So what we have to do, once we get the amplitude modulated wave, we have to remove its downward side, we have to remove its negative side to get the actual message signal. Okay. But there are some problems with this, because the lots of what we can say, the practical